Hi, I'm Eli Seidel.
And I'm Brad Lucas.
Our project entailed the investigation into the effects of Doppler shift on a visible light communication system.
A classic example of Doppler shift is how the pitch of an ambulance siren changes as it speeds past an observer. As the ambulance comes towards the observer, a higher pitch sound is heard, and as the ambulance passes an observer, a lower pitch sound is heard. These apparent pitch changes are due to the Doppler shift phenomena and can be applied to any type of waveform, such as light.
VLC is a method of communication whereby a signal typically in the range of 400 to 800 terahertz is transmitted via light. This type of technology makes use of light-emitting diodes for speeds of up to 500 megabits per second to transmit information. Electronic devices, known as photodiodes, are used to receive the light signal. For this project, an on-off keying modulation scheme was used to transmit a light signal. This is one method of how binary data can be encoded into light signals. By using OOK modulation, any alterations in the signal frequency spectrum would be as a direct result from the Doppler effect, and thus can be easily identified and addressed. A testbed is required in order to test the effects of Doppler shift on the communication system, by putting the transmitter and receiver circuits in motion relative to one another. Hi, I'm Eli Seidel.
And I'm Brad Lucas.
Our project entailed the investigation into the effects of Doppler shift on a visible light communication system.
A classic.
Our design used a bicycle setup, whereby the transmitter is mounted to the wheel of the bicycle. As the wheel spins, the transmitter will move past the stationary receiver with a speed equivalent to that of the wheel's tangential velocity. This setup is tested up to 80 km per hour, and the speeds are measured via a commercially available speedometer.
The design transmitter circuit makes use of a TNC 4.0 to produce a PWM signal. This square wave signal represents the on-off keying method that is used in this project. A driver circuit is used to ensure that the output LED completely turns on and off to accurately produce a square wave light signal. This circuit is made portable via a power supply to ensure that the transmitter can easily be put in motion relative to the receiver. The receiver detects the light being transmitted via a transimpedance amplifier. This form of circuitry consists of a photodiode and an op-amp that converts a received current signal into a voltage signal that can be sampled and processed digitally. The signal is further conditioned to mitigate any noise from ambient light that may distort the received signal. The final conditioned signal is sampled via a Tektronix 5 series oscilloscope, which was able to sample the signal at 625 megasamples per second. The recorded signal then can be later analyzed for any shifts in frequency.
The normalized time domain signals for the tests run at 1 MHz at 0 km and 80 km towards and away from each other are represented below. It is evident that the general waveform of each graph are similar to one another. The graphs are overlaid and look shifted. However, this is due to their point in time at which the recordings took place. Attention should be paid to the width of the waves in order to determine whether there is a frequency shift or not.
The following graphs represent the frequency content of the time domain signals presented on the previous slide. As one can see, the frequency content follows that of a 1 MHz square wave as expected. At 1 MHz with a relative speed of 80 km per hour, one will see a frequency shift of plus minus 0.0741 Hz. The resolution of the Tektronix scope does not cater for the required high precision resolution measurements to sufficiently determine an accurate frequency shift. One can use these types of results as a proof of concept. However, future iterations of this project will require a more sophisticated measurement system.